Good morning, students. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, we will see about the mechanical properties of solids. If I say mechanical properties of solids, it includes stress, strain, creep, hardness, resilience, etc. Let us see the mechanical properties of solids one by one. So, as we know, solid has a definite shape and size. In order to change, that is, in order to deform the shape or size of a body, a force is required. Whenever a force is applied, then only the shape or the size or the solid is said to be deformed. For example, if you stretch a helical spring by gently pulling its ends, the length of the spring increases slightly. This obviously everybody knows. If you elongate or if you stretch, the spring gets elongated. If you remove the stress, it comes back to the original position. So when you leave the ends of the spring, it regains its original size and shape. This generally we observe in case of elastomers, that is rubber material. The property of any object for which it tends to regain its original size and shape when the applied force is removed, it is known as elasticity, and the deformation caused is known as elastic deformation. This type of deformation, it is generally observed in any elastic material, so it is called as elastic deformation. However, if you apply force to a lump of mud, it has no tendency to regain its previous shape and it gets permanently deformed. Such a substance is called plastic and the property is called as plasticity. I hope you have understood these two, the term elasticity and plasticity. In case of elasticity, once it is deformed, it can able to regain its original shape, whereas in case of plasticity, once it is deformed means deformed only. It is permanently deformed. Regaining is not at all possible in case of plasticity. That is the basic difference between elasticity and plasticity. The elastic behavior of materials plays an important role in engineering design. For example, while designing a building, knowledge of elastic properties of the material like steel, concrete is essential. The same is true in case of designing of bridges, automobiles, ropeways, etc. So one could also can ask, can we design an aeroplane that is very light but sufficiently strong? So the driving force behind elastic behavior of solid, what is it? Let us see. In a solid, each atom or molecule is surrounded by neighboring atoms or molecules. That's why in case of solids, the atoms are closely packed, more rigid. These are bonded together by interatomic or intermolecular forces and stay in a stable equilibrium position. When a solid is deformed, the atoms or molecules are displaced from their equilibrium positions, causing a change in the interatomic or intermolecular distances. When the deforming force is removed, the interatomic forces tend to drive them back to their original positions. Thus, the body regains its original shape and size. That is why, in case of elasticity or elastic material, which are able to regain its original position. Let us move on to the next property, stress and strain. Let us see one by one. First one is stress. When your body is subjected to a deforming force, a restoring force is developed in the body. This restoring force is equal to the magnitude but opposite in direction to the applied force. The restoring force per unit area is known as stress. If F is the force applied to a cross section of a body having a area A, then stress is equal to F by A, that is force divided by area. The SI unit is Newton per meter square or Pascal. There are different types of stresses. One is tensile, shearing and hydraulic stress. Let us see one by one. There are three ways in which a solid may change its dimensions when an external force applied on it. For example, if your body is stretched by two equal forces applied normal to its cross-sectional area, the restoring force per unit area in this case is called as tensile stress. If the object is compressed under the action of applied force, then the restoring force is known as compressive stress. And then the third one, tensile or compressive stress can also be termed as longitudinal stress if the change in the length, that is delta L, to the original length of the body is known as longitudinal strain. Whatever the changes that is occurring, that is called as strain. That is longitudinal strain is equal to delta L divided by L. If a deforming force is applied parallel to the cross-sectional area of a body, there is a relative displacement between the opposite faces of the body. The restoring force per unit area developed due to the applied tangential force is known as tangential or shearing stress. So the strain so produced is known as shearing strain, that is given by delta x by L, which is equal to tan theta. Then next one is hydraulic stress. If a force is applied on an object at each point of the surface and the body is said to be under hydraulic compression, this leads to decrease in its volume without any change in its geometrical shape. The body develops internal restoring forces that are equal and opposite to the applied forces. The internal restoring force per unit area, in this case it is called as hydraulic stress. So if an object is placed under a fluid, so volume strain is equal to delta V by V. Next we will see about the Hooke's law. Stress, that is the pressure experienced by an object, is the action, and strain is nothing but dimensional changes. Stress is the cause and strain is the result. For small deformation, the stress and strain are proportional to each other. This is known as Hooke's law. Therefore, can be written like this: stress is directly proportional to strain, or stress is equal to K into strain. K is a constant, that is modulus of elasticity, where K is the proportionality constant and it is known as modulus of elasticity. So this is the important graph, stress strain curve or stress strain plot. Here stress is plotted against strain. Several points are mentioned here. What is A, B, C, D and E? We'll see one by one. So this is the typical stress strain plot or curve for any given material or metal. The relation between the stress and strain for a given material, it may be metallic wire, under tensile strength can be found experimentally if the applied forces gradually increase in steps and the following changes in length are noted. If we increase the force, applied forces increase, then what are the changes that is occurring in terms of length? That is what depicted in this plot. The stress strain curves vary from material to material. It helps us to understand how a material deforms with increasing load. The origin O to A in the curve is linear. As you see here, O to A from here, this vertical line, it is linear. What is it meaning? Till O to A, Hooke's law is maintained. Hooke's law is obeyed means stress is directly proportional to strain. That is Hooke's law. The material regains its original dimensions when the applied force is removed. In this region, the solid behaves as an elastic body. Whenever it tries to regain its original position, then it is nothing but elastic nature or elasticity. So the point A up to which it obeys Hooke's law is known as proportional limit. So O to A, it is known as proportional limit. So the region A to B, O to A, what we have seen, it is proportional limit. Stress is directly proportional to strain. Then A to B. Let us move on to A to B. So the region A to B, stress and strain are not proportional, but the body still returns to its original dimension when the load is removed. Point B in the curve is known as yield point, or it is also known as elastic limit. O to A proportional limit, whereas B is known as yield point or elastic limit, and the corresponding stress is known as yield strength of the material. If the load is increased further, the stress developed exceeds in the yield strength and strain increases rapidly, even for a small change in the stress. The portion of the curve between B and D shows this. B to D. The strain increases. When the load is removed, say at some point C between B and D, body does not regain its original dimension. So between B and C, the body is not able to regain its original dimension. In this case, when even when the stress is zero, the strain is not at all at zero. The material is said to have permanent set. The deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength of the material. Beyond this point, that is beyond this point, additional strain is produced even by a reduced applied force and fracture occurs at point E. So this point E is known as fracture point. If the ultimate strength and fracture point D and E are close, the material is said to brittle, fractured, so brittle in nature. If they are far apart, the material is said to be ductile. So let us see further explanation of brittle and ductile nature. If the ultimate strength and fracture points are close, the material is said to be brittle. If the ultimate strength and fracture points are far apart, then the material is said to be ductile. Generally, ductile materials will withstand large strains before the specimen ruptures. Brittle materials fracture at much lower strains. Brittle materials often have relatively large Young's moduli and ultimate stresses in comparison to ductile materials. Bone, cast iron, ceramic, and concrete are examples of some of the brittle materials. Materials that have relatively large plastic region under tensile stress are known as ductile. Examples of ductile materials it includes aluminum and copper. So as you can see, stress strain plot, this region is brittle, after that it is ductile in nature. Let us see the stress strain plot of any elastomeric material. Elastomer, already I told you, well known example is rubber. So rubber can be pulled to several times its original length and still returns to its original shape. So this figure it shows stress strain curve for the elastic tissue of aorta present in the heart. Although elastic region is very large, the material does not obey Hooke's law. What is Hooke's law? Stress should be directly proportional to strain, whereas here it is not so. There is no well-defined plastic region. Substances like tissue of aorta, rubber, etc., which can be stretched to cause large strains called elastomers. The next one is tensile strength. When stress continues in the plastic regime, the stress strain passes through a maximum called the tensile strength and then falls as the material starts to develop a neck and finally breaks at the fracture point. This is called as necking. In plastic deformation, after the ultimate tensile stress, the value of stress strain falls down, it forming a neck-like structure which is known as the neck, the point of necking. See this portion. After UTS, the material starts to rupture and the point reached where it finally breaks is called the fracture point. Next one, the elastic moduli. The proportional region in the stress strain curve, that is already we have seen a region OA, O to A. The ratio of stress and strain called modulus of elasticity. It is found to be a characteristic of the material. Young's modulus, the expression is given by the ratio of tensile or compressive stress to the longitudinal strain. Epsilon is defined as the Young's modulus and it is denoted by the symbol Y. So Y is equal to sigma by epsilon. Since strain is a dimensionless quantity. The unit of Young's modulus is same as that of stress, that is Newton per meter square or pascals. So the next property, resilience and toughness. So resilience is basically, it is defined as the capacity of a material to absorb energy when it is deformed elastically, and then upon unloading to have this energy recovered. In other words, it is the maximum energy per volume that can be elastically stored. It is represented by the area under the curve in the elastic region in the stress strain diagram. This region is known as the shaded portion, that is called as resilience. The ability of a metal to deform plastically and to absorb energy in the process before fracture is termed toughness. The emphasis of this definition should be placed on the ability to absorb energy before fracture. Let us recall ductility. It is a measure of how much something deforms plastically before fracture, but just because a material is ductile does not make it tough. The key to toughness is a good combination of strength and ductility. A material with a high strength and high ductility will have more toughness than the material with low strength and high ductility. Therefore, one way to measure toughness is by calculating the area under the stress strain curve from a tensile test. This value is simply called material toughness, and it has units of energy per volume. Material toughness equates to slow absorption of energy by the material. Next important property of solid is impact strength. Let us see what is impact strength and the factors affecting it. Impact strength, also called impact toughness, that is, it is the amount of energy that a material can withstand when the said load is suddenly applied to it. So impact strength, till what extent the material can withstand the load, that is called as impact strength. It may also be defined as threshold of force per unit area before the material undergoes fracture. The strength of materials may be defined in many ways, and some of the most common parameters include tensile strength, yield strength, and creep limit. These material strength properties involve the gradual application of force until the material breaks or show deformity. So some of the factors: temperature and material thickness. Impact strength increases with increase in temperature. Material thickness, with respect to material thickness, increasing the thickness reduces impact strength. At low temperature, material is more brittle and impact toughness is low. At high temperature, the material is more ductile and the impact toughness is high. The transition temperature is the boundary between brittle and ductile behavior, and this temperature is often an extremely important consideration in the selection of the material. The next property is creep. Creep is nothing but it is a slow and progressive deformation of a material with the time under constant stress. So here the stress is nothing but again applied load only. It is performed at a constant temperature. The rate of deformation is called the creep rate. It is the slope of line in the creep strain versus time. So you can see the plot over here, strain versus time. So you have initial strain, in that you have elastic and plastic behavior. This region, primary creep, then C to D it is secondary creep, then D to E it is tertiary creep, after E it is rupture. So the different stages of creep: at the very initial stage, an instantaneous elastic deformation, that is A to B. A to B elongation is observed when a load is applied, and then primary creep, it starts at a rapid rate and slows with the time, that is A to C, includes instantaneous elastic deformation, and then the secondary creep, steady state creep, secondary from here to here, has a relatively uniform rate, that is C to D, and then the tertiary creep here between T to E. It has an accelerated creep rate and terminates when the material breaks or ruptures. It is associated with both necking and the formation of grain boundary voids. So in this slide, you can see the effect of temperature and stress. Higher the temperature or high stress, medium temperature, medium stress, low temperature, low stress. Then the next property is hardness. So hardness, it is the resistance to plastic deformation. Therefore, it is a measure of plastic deformation. Historically, it was measured on an empirical scale determined by the ability of material to scratch another, that is diamond being the hardest and talc the softer. Now we use standard test where a ball or point is pressed into a material and the size of the dent is measured. Hardness is the resistance of a material to localized deformation. The term can apply to deformation from indentation, scratching, cutting, or bending. In metals, ceramics, and most polymers, the deformation considered is the plastic deformation of the surface. For elastomers and some polymers, hardness is defined as the resistance to elastic deformation of the surface. The lack of fundamental definition indicates that hardness is not a basic property of a material, but rather a composite one with the contributions from the yield strength, work hardening, true tensile strength, modulus, and other factors. Hardness measurements are widely used for the quality control of materials because they are quick and considered to be non-destructive tests when the marks or indentations produced by the test are in low stress areas. Let us see the last property, fatigue. Fatigue is defined as the process of progressive localized plastic deformation occurring in a material subjected to cyclic stresses and strains at high stress concentration locations that may culminate in cracks or complete fracture after a sufficient number of fluctuations. Fatigue is a form of failure that occurs in structures subjected to dynamic and fluctuating stresses. For example, bridges, aircrafts, machine components, etc. Under these circumstances, it is possible for failure to occur at a stress level considerably lower than the tensile or yield strength for a static load. The term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stress or strain cycling. Fatigue is important as much as it is the single largest cause of failure in metals, estimated to be involved in approximately 90% of all metallic failures, even some polymers and ceramics also, except glasses. So fatigue is occurring very suddenly and without warning. Fatigue failure is brittle like in nature and even in normally ductile metals, in that there is very little gross plastic deformation associated with the failure. The process occurs by the initiation and propagation of cracks, and typically the fracture surface is perpendicular to the direction of an applied tensile strength. Some more information regarding fatigue. Material fatigue is a phenomenon where structure fail when subject to a cyclic load. This type of structural damage occurs even when the experienced stress range is far below the static material strength. Fatigue is the most common source behind failures of mechanical structures. Several terms are there. The stress varies between maximum and minimum stress during a load cycle. Each and every load is given like this with the crust and trough areas. In the field of fatigue, the variation in the stress is often defined using the stress amplitude and the mean stress. Further variables defining the stress range, that is delta sigma and the R value, are frequently used to describe the stress cycle. The most important parameter for fatigue damage is the stress amplitude. For any detailed analysis, the mean stress however, must be taken into account as well. Tensile mean Tensile mean stress increases the sensitivity to fatigue, whereas the compressive mean stress allows for higher stress amplitudes. So in today's class, we have seen some of the mechanical properties of solids, which includes stress, strain, creep, hardness, impact strength, and then finally fatigue. I hope you have understood today's class. Thank you.